Hey guys, welcome to a new video. In this video here, we're going to take a look at how we can do object detection on very small objects. So in one of the previous videos, we went over the SAHI model and SAHI framework, so you can actually just divide your image into individual tiles. Then we have a single tile just sliding over a whole window, and then we do inference on each individual tile. Of course, this is going to take longer to process each individual image, but now we're able to do object detection and detect even the smallest objects in our images. So this is very useful in a lot of computer vision applications and projects where we don't really need that real time. We're still able to squeeze out a couple of frames per second, but we won't get like 30, 60, 90 frames per second because we have to do the processing on each individual tile. Then once we have the tiles and the predictions in each individual tile, we just need to rescale the values back into the global frame, and we pretty much have all our detections. So let's just jump into the code. I'm going to show you how we can do it from scratch, so we're not using the SAHI framework, and also how we can run it on videos and a live webcam. So let's just jump straight into the Python script. I'm going to show you how we can do this tiling window inference on a live webcam and also stream, where we're going to go over the code, the functionality, and also how we can divide our image into tile, rescale our coordinates back into the global frame as well. So this is pretty much all the code. Doing that, you can modify it, you can process it on your own. We don't have any framework at all. This is custom implementation. We're going to process this with you here, and we're also going to see how we can run it on a live webcam. So if you're just running this through a YOLOv8, YOLOv9, you can take whatever object detection model that we have out there. It is only going to detect the cars and also the trucks in the front of the image here, and the ones up here at the top. It's not going to detect those. Those are just too small, even though with the human eye, we can easily see them. So this is kind of like the trade-off when we're doing object detection and so on, and it really depends on the objects that you want to detect. So right now we can still visually see these cars, but there could be instances, there could be classes and objects where we can't really see it with the human eye unless we zoom very far in. So we really just go down on a lower pixel level when we're doing inference with our object detection model by using tiling windows. So let's now just go back to the code again. Let's go over it step by step so you guys can know how to implement it, how it works under the hood, and then we're going to see how we can run it and see the results. So first of all here, we're just going to import the different modules and the dependencies that we need. So OpenCV, from typing here, we're going to have the dictionary, list, optional, sequence, tuple, and so on. This is basically just for the format of our function. So we specify the input arguments, the data types for inputs, and also the outputs. Then we have PLL here. We need to convert it to PLL before we can go in and process it. We can also have like a for loop running through all of the code. We're going to use autolytics, so we can just take a YOLOv8, YOLOv9 model, and then we're going to process that on each individual tile. So we can go down on an even lower level and do this implementation ourselves, but then we need to take care of a lot of things. We can't do automatic slicing and all of those things. Right now we just have a single function. It takes in the image height, image width. So these are just two integer values. We have the slice height and also the slice width. So this will be our tile window size. So it's basically just one large image. We divide it into sub images, and then we just slide that over a whole image and basically just do a scan. Now we can also set the auto slice resolution. So if it just needs to figure out by itself how to do auto slicing directly in here, if you don't specify the slice height and also slice width. Another cool feature that we have is that we can specify the overlap width and also height ratio. It's basically just how much should each individual tile overlap each other, because if we just do detections on one tile here and another tile, we might end up cutting the object right in the middle. And to be able to get around that, we just need to have this overlapping region between our tiles, and it really depends on the size of your objects, types of your objects, and so on. But it is always pretty good to have like these overlaps. The code here will take care of all of that, so you don't go out of boundaries. You get the exact amount of slices. It will take care of all of that. You can also do the implementation yourself with just like 2 for loops, where you're just running through the whole image. You specify the slice width and also the slice height, and then you can do slicing with NumPy on each individual image. But then you can't really have like overlapping regions. You need to take care of like your slicing height and also slicing width. It should be within the boundaries. We can't really like have 1000 pixels in the X direction and try to slice it in 4 slices with 300 pixels in each, because that is going to overflow and go out of boundaries with 200 pixels. So this code here is taking care of all of that. So you can use this code here directly. It will be down in the description on my GitHub link. So first of all here, we just have all these different parameters, and it's going to return a list of lists with integers. So this is going to be our slice bounding boxes for our image. So first of all, here we just have our slice boxes. So we're going to find the boxes which we're going to do our slices for. We need to take care of our coordinates all the time. So the top left corner, we always look at the top left corner when we do our slicing in each individual image for the tiles. Then we just check here if we actually have something for the slice height and also the slice width. Now we go in and take care of how much overlap do we need to have in the Y direction and in the X direction. And that is just integer value of our overlap height ratio multiplied with our slice height. The exact same thing with our X value, so for our width. Now we have taken care of that, we can then go down and have a while loop just running through all the Y values. So right now we're just going to have our Y values. We set our X value equal to 0, and then we have our Y min plus our slice height. So it's basically just going to run through each individual pixel in both directions. So instead of just having, you can also have like 2 for loops instead of 2 while loops. But right now we just run through a whole image with the individual slices. Then we can go in and append the slice boxes. So right now it's just going to extract the values. So the min and also the max for our values. So we need the top left corner and also the bottom right corner. And then we have the slicing bounding boxes for our tiling windows. Then we go in and just append that to our slice underscore boxes, and that's pretty much it. So it's just a for loop, or like 2 while loops, 2 for loops, just running through the whole image, finding these slice bounded boxes. When we have that, we can go down and create a class. So right now we just have a class instance where we have an image and also starting pixel, because for every single tile, we need to know where that tile is starting, or else we can't really project and remap our coordinates from our predictions to the global frame again. And we want to do that. We don't want to just have individual predictions, because if you just have one tiling window, let's say it's 50 by 50, then you will get all your values, all your detections within that range. So between 0 and 50. But if you have like an image, which is 1000 by 1000, we will just have all the detections in the top left corner. So we need to take all of those detections, add it with the starting pixel, because then we basically just project and rescale all our coordinates back into the global frame. So right now we just have a class for a sliced image. So it's just going to contain the image and the starting pixel, so we can always retrieve that. Then we have our sliced image results, which is basically just going to contain our whole image. Then we can have a for loop running through that. So right now we have original image size and image directory. We can have multiple images. We can have a single image. We can just pull an image from a video or a webcam with OpenCV, convert it to PRL, and then it's going to take care of all of that. Then we have our sliced image list, which is the one that we're going to return. And then we can have a for loop running through each individual tile that our image has been divided into. Then we just have a function for adding a sliced image to our list down here. So a sliced image underscore list dot append, and the sliced image that we're going to get as an input argument to this function. Then we have our property functions down here at the bottom, which is basically just going to both return our sliced image list when we want to do inference on our tiles. We have our images here. So if we just have like an image list, we can just go through all of that. We can take the image. So right now inside our sliced image, we both have the image, but also the starting pixels. So this is if you just want to return a list with all the individual images. And then we also need our starting pixels. So these functions are the exact same thing. The only difference is that we now get the starting pixel instead of the image. We can also extract the file names. Same code, just a for loop running through all our sliced images, retrieving that information, both our starting pixels, the file name, and also our image or our tile. Then we can go down and create a function for getting an item. So once we want to get an item, do a next iteration in our list, it's just going to return a dictionary with our image. Then we just need to specify the index of the image or the tile that we want to extract from our class, and then it's just going to return a dictionary with the image and also starting pixel. We go in and index the images and also our starting pixels, where these lists here, they come from the other functions where we extracted all the information from the image and also the starting pixel. Then we basically just have some checks for if it's a numpy array. If it's like an integer value, then we can just call these functionality that we have up at the top here. For example, here we just check if our instance or index right now is a slice. And if it is slice, we're going to get the length of it. We're going to get the indices with our start, stop, and step. So this is just like the range of the for loop that we're going to run through. And then we can prepare the ith dictionary with our images. So we'll say that we have 10 slices that we want to run through. Then we have like a 1, 10, and then we have a step size of 1, and then we can prepare each individual tile, and then we just extract a list, return the list with each individual tile or like our dictionary, because it's going to return this one up here at the top when we call prepare ith dict Then we can go inside the dictionary and extract our image and starting pixel. So that's pretty much it. We can also extract the length of it. If we just call the length, we get the number of tiles that we have divided our image into. Now we have our slice image here, which is just going to use all of the classes and functionality that we have above. So we have our image, slide height, slide width, and so on. So these are the exact same parameters. It can also go in and do auto slicing based on the resolution if you want to use that. Then we can specify the minimum area ratio for the tiles that we want to use as well. So all of this functionality is already in there. We don't need to take care of that, and it's very useful. So right now, it's just going to take the image, take the PLL image, get the image height and also the image width. You can probably convert it to NumPy directly as well, so you don't have to do conversion later on. But this really depends on if you're doing like single image processing, or batch processing could also be like on live video streams as we're doing in this video here, just to show you guys, okay, how can we actually like set up the whole code base here? How can we just take an image, doesn't matter where it comes from, how can we take an image, process it with this tiling window method, the method behind SAHI, and do object detection on very small objects. So now we're just going to call our function, so get slice boxes. We get our slice boxes, which we're going to use later on. Now we can go in and create our slice image result depending on the original size. So that's what we have here. Then we have our sliced image results, which is just a list of all our images. Then we need to have a for loop running through all the slice boxes. We have our full image, we have our bounding boxes for our slices. Now we need to go in and actually like slice those with NumPy. So right now we're just going to have a for loop running through all of it. We have our top left corner, our bottom right corner, the XY value for those. So that's pretty much everything that we need. Then we have our original image. We go in and do the slicing. So we take the top left Y value and go to the bottom right Y value. And then we do the exact same thing with our X value. So it's basically just how do we extract the range for our image inside the tile. So this is how we can do slicing with NumPy. And it's going to take the window. So this will be our image sliced for the first sliced box that we have extracted. And then it's just going to do that for the X number of slices that we want to divide our image into. So that could be 10, 20, 5, 3, whatever you want to use, depending on the resolution and also how small objects you want to detect. Then we have our slide width and our slice height. We create an instance of our sliced image with each individual slice that we have. And then we just append that sliced image to our sliced image result, and we can return that. So right now here at the bottom, it's just going to return a list with each individual tile inside that list. Then we can have a for loop or index that list directly to extract the individual slices. So that's pretty much it. That's the whole functionality behind SAHI. I've extracted the code here, basically just to show you guys like how can we run through it, how can we just take an arbitrary image, throw it through the whole pipeline and get the results instead of wrapping this around like multiple different frameworks. If you're using SAHI, it only works on a single image. It is not really general. You have to do specific modifications depending on the object detection model that you want to use. Right now, we just need to take the image, throw it into it. Doesn't matter what object detection model, segmentation model, whatever you're using, you can throw it directly into this code. Now we set up a video capture with the video that I showed you guys at the start. We create an instance of our model with YOLOv8. We have our while loop, just opening up our webcam. And as long as that is open, we're just going to iterate inside our while loop. We take the capture, we read an image from our capture. It could be a video file or a live webcam. We start a timer here just to see how many frames per second are we actually able to process. We convert our frame to a PLL image, we extract the height and the width, and now we specify the slide height and also slide width. So that is really a parameter that you need to specify on your own. Right now, I'm just dividing the image into 4 parts. So basically just take the height and the width, slice it by 4, and then we're going to get our tiles based on that. Then we call a function slice image. We specify the parameters. Right now, it's just going to use some overlap as well. You can also just specify 0 depending on the use cases that you have. Let's just start with a small overlap here. And then you normally, if you have double detections, you will go in and use non-maximum suppression to filter those out. But let's just have some overlap in this example. We get the number of tiles, so we can show that later on. Then we have our results list for the bounding boxes, confidence score, class IDs, that we can use it in our own applications and projects, how we can extract the results from the prediction from Autolytics. So now we have a for loop, we have an enumerate, we enumerate through our sliced image results. So we both get our I for index and we get our image slice, which is actually like slice inside our image. Now we can go inside our sliced image, we have a dictionary, as you remember, we have the image, and we have the starting pixel, so we know how to convert it back to the global image frame again. We have our window, start X, start Y. We do our prediction on our window. We can specify the confidence score here directly. We can probably just have that a bit higher, so 0.20, default is 0.25. We now have our results variable, and we need to know how to run through that. Inside of Walktrough documentation, you can find how to actually like extract them if you're doing segmentation, tracking, object detection, and each individual class and attribute in there. So now we just have a for loop running through each individual result. We extract the bounding boxes. So when we do object detection, we need to go in and extract results.boxes. Then we get our boxes where we can go in and extract the XY. So it's the top left and bottom right corner, the confidence scores, class IDs for each individual prediction that we have. So to be able to extract the XYs, we need to go in and take XY.xy. So this is just an attribute to this box class. We convert it to CPU. If you're using GPU to process our image, we need to convert it from GPU to CPU. And then we convert it to NumPy, so it's just easier to work with OpenCV. Then we check if the size is equal to 0, because again, if we're not detecting any boxes, we just want to continue to the next result that we have inside our results variable. We extract the XY, we get our confidence score, we do it in the exact same way. We can extract the class ID. There's also a bunch of other attributes that you can extract. You can find all of that on the Walktrough documentation. Then we're going to have a for loop running through all the XYs. So this is pretty much just all our bounding boxes, and for each individual bounding box, we can also extract the confidence score and the class ID. So we extract X1, Y1, X2, and Y2, because now we need to go in and actually scale it back. So right now we have the global frame, then we just have a small tile. We take the top left corner, and we need to actually just rescale it all the way back by adding this start value for our window. So this is something that we have to do to be able to have our detections in our original image. Convert it to integers again, and then we can go in and append a list with our bounding boxes to the boxes list, confidence scores, and class IDs. And now we have all the results extracted, and we can use it in our own applications and projects, either to do some triggering, alert systems, whatever you want to use it for, tracking systems, counting systems, and so on. So that's pretty much it. We have extracted all the results. We're ending the timer because right now it is just like looping through the results, visualizing them, or if you want to do something else with them. Now we have a for loop again, just running through all the bounding boxes. So this is just for visualization. Bounding boxes, we take the ith elements. So we're just going through all of them, extract the bounding box, confidence score, and class ID. And then we just have a rectangle with our bounding box on top of each prediction. And then we just put some text out here. We specify the class ID and also the confidence score, number of tiles in the top left corner together with the number of frames per second. At the end here, we just use OpenCV to show the frame where we're drawing all the results. If I hit Q on a keyboard at any time, you're going to break out of this while loop and terminate the program. So that's pretty much it here. We went through all of the code line by line so you guys can understand what is going on under the hood when we want to detect small objects. And I'm not just talking small objects, I'm talking very small object on very low detail. So we're operating on pixel level now, where normally if you're doing object detection, let's say that we have like a full HD image or like an HD image, so it's 1280 by 720. When we pass it through an object detection model like YOLOv8, it actually like downscales the images to 640 by 640 or like 640 by 480, depending on like what you specify. Could also be lower or higher depending on the model that you're using, but it actually like resizes and downscales the image a lot, where we lose a lot of information, and that's why we can't detect very small objects. So it's always a trade-off between like accuracy and speed. So now we just open up a new terminal here. I'm going to use Anaconda, and we can just run the Python script directly. So tiling.py, and we're going to use the video that we specified up at the top. Now I'm going to run it, and let's see the results with YOLOv8. So here we can see the results running. We can see it pretty much detects every single car, even the cars driving up here, which is pretty hard for just us to see. We can load a confidence score. We can also like use a larger model, but pretty much all the cars here, they have a confidence score at around like 0.80 to 0.90. So that's pretty cool. Now we're able to detect every single object in the frame. If you're not using tiling windows, it wouldn't be able to detect any objects above this line here. So all the cars in the background, it will not be able to detect those. This is really helpful for a lot of use cases and applications within the computer vision field, especially if you don't want to run real time. Right now you can see it processes around like 5 to 6 frames per second. I probably also have too many tiling windows or like tiling windows. So right now the frame is divided into 27 tiles, also because we have the overlapping region with 20%. We could probably lower this significantly more, maybe just like have a few tiles and it will still be able to do all the detections. 27 tiles being processed 5 times per second. So this is pretty awesome. Again, you can optimize the models. You can use the smaller ones depending on the hardware as well. Right now I'm running this on my 4090 GPU. We can see the image resolution that it throws into the model. You can see the inference speed and so on. So right now it processes it with only 4 milliseconds for each individual image that we pass through the model. So this is multiplied by 27, and then we basically just take a look at how many of those batches can be processed per second, and that is around 5 on a 4090 GPU. So you can probably not expect more than a few frames per second, probably like a bit higher if you're using like a lower amount of tiles. It doesn't have to be 27, it could just be a few tiles and you'll still get significantly better performance compared to just using the single image. Right now, just to end off the video, I'm just going to run it on my webcam instead, just to see how it performs on that one. We also have multiple different classes that we're detecting and not just cars. So we should just be able to specify a 0 for opening up our webcam. It should open up in just a second. There we go. I can just turn around. Of course, we're going to have a lot more detections. So this is only like a 640 by 480 image. We can also increase the resolution of that by just specifying the parameters inside, or like the settings inside of OpenCV, but let's not take too much into account with that. There we go. Let's delete the overlapping region as well, just to have less tiles. We should be able to process it. Right now it's a very small frame that we're basically just going to divide into a number of tiles. But we can see it's able to detect everything here. We get some double detections here and there because this keyboard will be basically divided into multiple different tiles. You can combine them, but this is mostly suitable for smaller objects and also if you have like very large image resolution. So just processing this video stream here would actually be doable with just a single pass. So we don't really need to use tiling window on this, but I just wanted to show you guys how we can run it on a live webcam, on a video, on an arbitrary image. You can take whatever you have. Right now we can even see it processed at around like 25 to 30 frames per second with 6 tiling windows. So it's going to take 6 windows, divide the image into 6 windows, throw it through the model, and it's doing that 25 times per second. So there's a lot of processing going on, and we can see it detects all the objects here pretty nicely. I can just move it around, get on top of it, TV, cop, person. We pretty much get all the classes in here, which is kind of like expected with the pre-trained model. So thank you guys for watching this video here. I hope you learned a ton. Definitely test this out if you have problems. I know a lot of you guys have reached out and have problems with detecting smaller objects in computer vision applications. So this is how you can do it. Use the code directly. It is pretty cool and you will get way better performance. Of course, you won't be able to run this in fully real time. So check it out. Everything will be on my GitHub. Go through it again. We went into details with every single line of code. I really like to create these technical videos where we really dive into code, explain step by step how does these models work under the hood instead of just using high-level frameworks where we need to do modifications here and there and we don't know what's going on under the hood. So I hope you've learned a ton. I hope to see you guys in one of the upcoming videos. Until then, happy learning. So we also have an AI career program if you want to learn how to land AI jobs and get AI freelance work. I teach you everything in there. We have programs, all my technical courses, weekly live calls, personal help, and I'd love to have you guys in there, help you out in any possible way. You can check out the program down in the description and the community, and then I'll just see you guys in there.